I welcome you in this lecture of fluid mechanics, where we are going to discuss some aspects of fluid kinematics. In kinematics, we understand the motion of the fluid particles and its consequences without considering the force. So in this chapter we shall discuss these points. First we shall discuss about the two approaches which are utilized for describing the fluid flow field. One was given by the Lagrangian in the year, which we shall discuss later on. So this was the Lagrangian approach, and another approach was given by the Euler. So that approach is called Eulerian approach or Eulerian description. Both are used for describing the fluid flow phenomena, and there is one more concept that is termed as material derivative or total derivative, through which we try to transform conservation equations from Lagrangian approach to Eulerian approach. After that we shall discuss three types of lines. These are known as streamlines, streak lines and path lines, which are used for analytical analysis as well as for flow visualization. After that we shall discuss some fundamental kinematic properties. When fluid flows, then there may be translation, rotation, linear strain rate and shear strain rate. So how to quantify these rates with the help of some governing relationship, or how to define these strain rates. Then we shall discuss the concepts of vorticity, rotationality and irrotationality. After that we shall discuss very famous theorem which is termed as Reynolds transport theorem, or in short we call it RTT, which is utilized for transforming the equations from system property to the control volume property, because in many situations we use the control volume approach. So in that approach we have to convert the control volume properties to the system properties, because all governing equations are related to system properties. So these are the things which we shall discuss in this chapter. So let's first start with the velocity field. In velocity field, with the help of this figure, we want to understand what is the meaning of velocity field. So let's consider we are sitting in this room or wherever you are sitting. We can define the x coordinate, we can define the y coordinate, and we can define the z coordinates. So we are in a Cartesian coordinate framework, and in this region some fluid particles which occupies this position at certain time t, and name of this particle is, let's say, A. Then the position vector RAT define its position at this time. After certain time it follows certain path and it reaches to this location, and position vector of this location is defined by position vector that is written as RA t plus delta t. So this is the position at time t plus delta t of same particle, which was here at delta t times ago. So in this manner we can define the velocity field, and for Cartesian coordinate system mathematically we can represent, suppose this is the path followed by certain particle over the time. So at a given time this particle is having this v velocity. This v has three components. In x direction it is u at this time, and in y direction it is v, in z direction it is w. So for Cartesian coordinate system, where unit vectors are defined by I cap, j cap, k cap, velocity is represented mathematically by this equation: u xyz ti plus v xyz ti plus w xyz ti, tk, where u is, though it is a velocity in x direction, but it is function of xyz, means it varies from point to point, and it is function of time also. Similarly, this v is function of xyz and time. Similarly, this w, which is the velocity in z direction, but in the flow field it is varying, and it is function of what? It is function of x, y, z and t. So this velocity field can be represented by this equation. Now we are going to discuss the two important methods which are known as Lagrangian method and Eulerian method to describe the flow field. Both were mathematician. Lagrange was the Italian mathematician who lived from 1736 to 1813, and he proposed this method where all individual fluid particles, as they move about in a flow field, their fluid properties are associated with these particles only. Over the time. So in this case, where we call it Lagrangian description of flow motion, we follow the particles, and over the time its properties are observed, and this description is termed as Lagrangian description. Then another method was proposed by Leonhard Euler, who was Swiss mathematician, lived his life from 1707 to 1783. He proposed that instead of following the particles over the time in flow field, let's fix certain point which may be termed as a infinitely small control volume, and all properties of that flow domain is described by observing those properties at those fixed locations, like it is shown with the help of this figure. Here fluid is flowing like this, and simply it is a two-dimensional flow. So we have a x coordinate, we have a y coordinate. So if we define certain point here which is having x0 coordinate and y0 coordinate, and this infinitely small control volume fixed. So here if temperature is measured over the time, means it will be measured only at this point. So many particles will move from this point O, and they will occupy different position at different location after certain time, but we will observe all the properties at this location only. Whatever particles comes and goes, but we will keep more observing the properties at this location. So suppose let's say we are observing temperature only. So at temperature T over the time at location which is designated by x0, y0, and it is since function of time also, so this is represented as t x0 y0 time. This is the property, and which property we are measuring here? Let's say temperature. So temperature is written as t x0 y0, which is the position of the point or very infinity small control volume, and time. This is termed as Eulerian approach. So in flow field we can have n number of these points where we observe the property, and in that manner we define the flow field. Now another approach is Lagrangian approach, in which let's say this is particle A. This is very infinity small particle A, and over the time, suppose this was the position at certain time of same particle A, it is traveling in this flow field. So over the time, if we measure the property of this particle, we tag this particle, and over the time we are measuring this property, let's say temperature of the same particle. So here we are following the particle. We have not fixed the location as we did in case of Eulerian approach. So here we have a particle A, and this over the time it is moving, and as it is moving we are observing its property over the time. So this is represented here Ta, means temperature of this particle A over the time, its property, let's say temperature, is written as mathematically Ta small time, temperature. So these are the two different approaches to describe the fluid motion, but generally in fluid mechanics we use the Eulerian approach because here number of points in which we are interested, we can fix those points, and correspondingly we will have equation and we can solve those equation for the desired property which we want to investigate for the flow field. But in case of the Lagrangian approach, since number of particles are large in fluid mechanics and each particles consist of millions of molecules. Okay, so since number of particles are large, we will have very large number of equation, and it will become very difficult to solve those equations. But wherever we think that number of particles are less, where continuity equation or say continuum does not hold good, then naturally we have to go for the Lagrangian approaches to solve for different fluid properties. Okay, so here we have understood what is the difference between Lagrangian approach and Eulerian approach for describing the fluid flow region. Then we shall discuss three lines which are known as streamlines, streak lines, and path lines. These lines are used for describing the motion of particle, and these lines helps in visualizing the flow particles, or even this streamline is particularly used for analytical purpose also. So what is the definition of these lines? Streamline is defined in such a manner, so in any flow field, if we draw tangent in that flow field, if you describe certain line, and on that line if we draw the tangent, suppose this is the line which is shown here with the help of black color over the time in this flow region which we are considering here only two-dimensional flow, so for sake of simplicity, and we are considering Cartesian coordinate system. And at this point, if we draw tangent, this is the tangent, and everywhere if you draw the tangent, then that tangent gives you the velocity field. In that case, this black line is termed as streamline. So for this streamline, if we draw this tangent of velocity, then velocity may be resolved in two Cartesian coordinate system, x direction and y direction. In x direction this is u, and in y direction it is v. Similarly, for a very small field, we will have this dx coordinate, we will have dy coordinate. So with the help of this figure, the equation of the streamline can be written in the form of dy over dx is the slope, and v over u is also slope. So it means that dy over dx is equal to v over u, which is the equation of streamline for two-dimensional flow. Then we have another line known as streak lines. This streak line is defined as when, suppose this is a nozzle, and through this nozzle several particles have emerged and they have taken different position. So this particle was emerged some time ago from here, and right now this is the position. The another particle emerged from here, and this is the location of this particle. Similarly, these are the location of the particles at a given time, but they all came from the same location. If we draw or take the instantaneous picture of all these points, then this line is termed as streak line. Right. Then we have path line. In case of path line, suppose this is the point, this is the point through which one particle has emerged, and over the time, this was in previous case, this was at that instant several particles have emerged and they have taken certain position. If you take the instantaneous picture or that point, then this line is called as streamlines. But here the particle has emerged and it has taken different position at different times. So right now it is here, but just before this it was here, before that it was here. So if we draw this line which is joining the position of the particle emerged from this location over the time, then this line is called path line. So it means that path followed by the points is called path line. Now with the help of simple analysis, you can say when flow is steady and uniform, then path line, streak line and streamlines, all three are same. But if flow is not steady and non-uniform, then all three are different. Right. So here we have learned about the definitions of streamlines, streak lines and path line. Now we shall discuss about one very important property where we are deriving relationship for acceleration, but it is valid for other field variables also. So here we are going to develop relationship for acceleration of a fluid particle in some velocity field. So here we are considering three-dimensional Cartesian coordinate system. This is x coordinate, this is y coordinate, this is z coordinate. In any flow field, this line is representing the particle path over the time. So this was the particle at time t, and the position vector of this particle at time t is r bar. After time delta t means t plus delta t is the time right now, this particle has moved from this location to this location, and whose position vector is represented by r vector plus dr vector. Right. So keep this figure in mind. Now we are going to derive relationship for total acceleration, or that is termed as material acceleration, or total derivative, or material derivative. So the point at point t is having velocity Vp. This Vp is represented by V x, y, z, t, because it is function of x, y, z and t. At time t plus delta t, since delta t dt means definition, it is infinity small time, that same point has moved to another location whose coordinate is now x plus dx, y plus dy and z plus dz. Right. So at this time the velocity is represented by Vp. Vp means velocity of that particle at time t plus dt is equal to, so velocity is function of x, y, z both and t, all three, 4. So Vx plus dx, y plus dy, z plus dz, and time is t plus dt. So in this case, you imagine, suppose this is a infinity small volume. By definition, you may call it as a point, but it has dx, dy, dz. By definition, these dx, dy, dz are infinity small. So some particle enters here, and that same particle goes from here. Right. So basically this is a contour volume, very infinity small contour volume, where velocity is varying. Means velocity at this point is different, velocity at this point is different. And by using the concept of differential element, we want to convert into differential equation. So here you have to keep this thing in mind. So here dp, if we want to know what is the change in velocity of that particle when it moves from point which was represented by position vector Ra to Ra plus dr, and dr may be represented by dx, dy, dz. So here velocity is function of what? Velocity is function of x, y, z and time. So with the help of chain rule of differentiation, we can find dv. This dv is equal to del v over del x multiplied by dx, del v over del y multiplied by dy, del v over del z multiplied by dz, and del v over del t multiplied by dt. Right. So total acceleration of the particle, which may be written as ap, so dvp over dt. By definition, this is acceleration, and here this is called total acceleration or material acceleration also. Total acceleration or material acceleration or material derivative. Now this total acceleration is equal to what? So divided by dt. So del v over del x multiplied by dx over dt plus del v over del y dy over dt. So in the right hand side you divide it by dt. Right. Now here look at this definition. What is dx over dt? So dx over dt is nothing but it is u velocity, means velocity in x direction. dy over dt is the velocity in y direction, and dz over dt is the velocity in z direction. So when we substitute the value of uvw by using this definition in this equation, this equation is reduced to this term. Acceleration is equal to u. This is now written as u by definition, u del v over del x plus v del v over del y plus w del v over del z plus del v over del t. Right. If we observe the right hand side of the equation, then this term, which is defined as total acceleration of a particle, is equal to, these three terms look same, and these are coming due to flux in x direction, y direction, z direction. So this is called convective acceleration. This is called convective acceleration, and this is called, this term is called local acceleration at that point. So with the help of this, let's try to understand what is the difference between local acceleration and total acceleration of a particle. This total acceleration of the particle sometimes is termed as total derivative also, because since we are writing this for acceleration only, but this is a generalized formula, and this term is coming due to convective. So if you have a flow field, then this term will come into picture. If you don't have flow field, means flow is steady and flow is uniform. In that case, if flow is uniform means velocity is not changing with position. So what is del v over del x? When v is not changing with position, it means that flow is uniform. So this term is 0, this term is 0, this term is 0. If flow is uniform, it means that del v over del s is equal to 0. So this term will become 0 if flow is uniform, means everywhere velocity is same at different location. If it is steady also, then properties are not changing with time. That is the meaning of steady. So if it is a steady, in that case this term is also 0. So acceleration is 0. But suppose it is steady and it is non-uniform. Non-uniform means del v over del s is equal to not equal to 0. In that case, this term exists, which is due to convective and steady, but this term will remain 0 because flow is steady. So this convective term will give you acceleration. So here let's focus on one important point. What is the difference between this term and this term? When we are following the particle, then this acceleration is due to following the particle. When it moves from x point to x plus delta x, or y plus delta y, z plus delta z. So we are following the particle here. This is of particle in that flow field, and this is the local acceleration at that point. So this is the point property, and this is the material property or that mass property which is moving from one location to another location. So this is may be termed as Lagrangian approach, and right hand side may be termed as Eulerian approach. And this term is coming due to flux. Right. Now the same equation for other field variable, let's say for temperature, can be written like dt over d small time, means this is time derivative of temperature, is equal to local derivative of temperature plus this is due to convective term. So in vector format this may be written as del T over del time, temperature, rate of change of temperature at that location, plus V dot del T. V dot del T. In vector form, these terms can be merged and may be written as V dot del T. Again, I want to emphasize that this term is coming when we are following that particle, and this term is when we are at a given location, and this term is because of the flux. Right. Now we will discuss one numerical, and I want to tell you one important thing here. In exam, if you have the question in which you are asked to explain the total derivative, local derivative and convective derivative, then most of us write it correctly. But if a numerical is given, then many students find it difficult to figure out which term is total derivative in the numerical or which term is local derivative in the numerical. So we will try to understand this term with the help of simple numerical, in which in winter the Gangetic plains experience cold winds blowing from the Himalayas, which brings about dramatic decrease in the local temperatures. At a given time, the temperature at Dehradun is 2 degrees centigrade. So here temperature at Dehradun is equal to 2 degrees centigrade, and Kanpur means, sorry, let's write this as capital T, which is term for temperature. At temperature at Kanpur is equal to 17 degrees centigrade, and distance delta x, or you can say x, is equal to 300 kilometer is given here. 2 degrees centigrade at Dehradun, distance is 300 kilometer, and temperature of the Kanpur is given 17 degrees centigrade. The average wind velocity is 40 kilometer per hour. So average wind speed velocity is also given. So let's say V is equal to 40 kilometer per hour. And it is observed that air heats up at the rate of 1 degree centigrade per hour. Now this is the question. What it is given here? It is heating up at the rate 1 degree centigrade per hour as it flows past the hotter plains. So this is the equation applicable. This equation is applicable here because we want to calculate for the temperature. So this term 1 degree centigrade per hour, this term 1 degree centigrade per hour, 1 degree centigrade per hour, whether dt over d small t is given or del t over del t is given, what it is. So as I explained you, this thing is called material derivative when we follow the particle as it moves in flow field. So in this case, as it flows, the air flows, it heats up at the rate. So it means what is given here? This is equal to dt over dt. Sorry, this may be written as d capital T, temperature, rate of change of temperature of that material. So this is given. Many students get confused. They sometimes they write this as 1 degree centigrade divided by 1 hour as small del T, small this thing which is equal to basically at a location. This is at a location, right? As it flows past the hotter plane. Find the rate of fall of temperature at Kanpur, assuming the temperature gradient between the two cities to be constant. And you have to find out the temperature at, you have to find out what? You have to find out rate of fall of temperature. So you have to find out del T over, so local rate of change of temperature at Kanpur. So this is to be calculated. So now you have this equation. This is the equation which we have to invoke. So here this is given, this is given, this is to be calculated, and only one dimensional velocity is given. So this may be put as 0, this may be put as 0. So you are left with this equation, dt over d time is equal to local rate of change plus u del T over del x. So this is given 1 degree centigrade per hour. Heats up means plus, if increase of temperature is taken as plus. Del T over del T at Kanpur is to be calculated. And what is u? Velocity in that direction. So this is given. So this is given. And what is del T over del time? This will be equal to 17 degrees centigrade minus 2 degrees centigrade divided by distance. So this is also given, and which is constant. So you can substitute here and you will get the answer, right? And I have given another numerical then. This previous numerical I have taken from Professor Gupta book, Vijay Gupta book, and second numerical I have taken from another book. You solve the second numerical.